Acids and bases and pH. When water ionizes, or you have a water molecule, H2O, that breaks apart and produces ions, which are charged particles, it releases an equal number of hydrogen ions, it's represented by H+, and hydroxide ions, that's OH negative. Notice also in this reaction that it's reversible. We see these double arrows so that water can break apart, producing hydrogen ions and hydroxide ions in a 1-to-1 ratio, or these ions can reform water. And so that's represented by this arrow that's going to the left. Sometimes ionic compounds, those that are formed by ionic bonds, dissociate. That's just a fancy word for fall apart, and release their ions when they are dissolved in water. A substance that does that is called an electrolyte. So for example, sodium chloride, table salt that we saw, is a good example of an ionic bond. Whenever you dissolve salt in water, you get a sodium ion and a chloride ion, right? So other common electrolytes found within body fluid include the magnesium ion, calcium ion, and potassium ion. Electrolytes that release hydrogen ions as an H+ in water are called acids. Electrolytes that release hydroxide ions, OH negative, in water are called bases. In 1909, a Danish scientist named Sorensen wanted to come up with an easy-to-use scale that would measure the strengths and weaknesses of acids and bases. He called it the pH scale because it measures the power of the hydrogen ion. An acidic solution, like we were just saying, is when an electrolyte releases hydrogen ions. So whenever that dissociates in water, you have a high hydrogen ion concentration. A good example of this is hydrochloric acid, represented here by HCl. Whenever that compound breaks apart in water, you get hydrogen ions and chloride ions. The key with acids is that you have a high hydrogen ion concentration. Bases, on the other hand, have low hydrogen ion concentrations. Bases are substances that when they dissociate or break apart in water, they release hydroxide ions or take up hydrogen ions. A good example of this, a strong base, is sodium hydroxide, shown here by NaOH. And whenever it is dissociated in water, you get a sodium ion and a hydroxide ion. So here we see that it releases hydroxide ions. Also, we could see that if we combined this hydroxide ion with a hydrogen ion, we would reform water. So it could also take up hydrogen ions, right? Bases are also known as alkaline substances. The pH scale, again we're measuring the power of hydrogen, goes from 0 to 14. From 0 to just before 7 is the region of the scale in which we find acids. The lower the number, the stronger the acid. So if you had something with a pH of 0, that would be strongly acidic. If you had something with a pH of 6.5, that would be mildly acidic. A pH of 7 is going to be neutral, in which you have a perfect balance between hydrogen ions and hydroxide ions. Pure water has a pH of 7 because it is a perfect balance between these two ions. Anything that is above 7 is going to be alkaline or basic. The higher the number, the stronger the base. So a pH of 14 would be a very strong base. This table from your book gives some examples of pH values in different common substances. So hydrochloric acid, as we just saw in our example, an example of a very strong acid, and sodium hydroxide being an example of a very strong base. So we can see how it varies in between here. Also on the subject of pH is the concept of a buffer. A buffer is a chemical or combination of chemicals that help keep pH within normal limits. Thinking back to chapter 1 and the concept of homeostasis, we have this ideal range, and buffers within our body, especially within our blood, is one way that we help maintain homeostasis. So a buffer, if it's going to keep pH within a certain range, it's going to be able to react with excess hydrogen ions or excess hydroxide ions, right? Because if you have something that's acidic, it's releasing an excess of hydrogen ions, or something that is basic, it's going to release hydroxide ions. So a buffer needs to be able to react with either one. So a good example is bicarbonate ions and carbonic acid that's found within our blood helps buffer the pH in blood to a pH of 7.4. Here's how it works. If hydrogen ions are added to blood, so something acidic, this reaction occurs. You have bicarbonate ions here that react with excess hydrogen ions, and then they form carbonic acid. If, on the other hand, you have hydroxide ions that are added to blood, so something basic or alkaline, this is the reaction that occurs. You have the carbonic acid that reacts with the hydroxide ions. That goes to form bicarbonate ions and water. So these reactions help prevent any significant change in blood pH. We start to have problems if our blood gets either too acidic or too alkaline. Types of chemical reactions. Cells commonly use reactions to join monomers. Now a monomer, if we think of mono meaning one, it's a simple organic molecule that exists individually, like a single building block. But a polymer, poly meaning many, are large organic molecules formed by combining monomers. These are the macromolecules that we're referring to within organisms, and they contain many molecules joined together. In order to make these macromolecules, we have synthesis reactions, in which simple substances combine to form a more complex substance. For example, when two hydrogen atoms and one oxygen atom combine, they form water. When two monomers join together in a dehydration reaction, an OH and an H, which are the components of water, right? They're removed as a water molecule. This is a type of synthesis reaction. We'll see this momentarily. Two other types of chemical reactions to keep in mind as we go along are decomposition reactions and reversible reactions. Decomposition reactions are just the opposite of synthesis reactions. Instead of building something as we are in a synthesis reaction, now we're taking it apart. So in a decomposition reaction, complex substances break down into simpler ones. For example, when a protein breaks down into amino acids, we'll see here in a few slides how amino acids are the monomers of the polymer that is a protein. In a hydrolysis reaction, you have the components of water are added, and this is a type of decomposition reaction that we'll also see momentarily. For a reversible reaction, simple substances form more complex substances, then turns right back around and breaks down into simpler ones. This is represented by reaction arrows that point both directions. So sodium chloride, right? So our components here, the sodium ion, chloride ion, if it is a synthesis reaction, we form sodium chloride. If we went the other way, decomposition reaction, we get the ions. This double arrow represents a reversible reaction. We also just saw this whenever we were looking at the concept of pH and how water ionizes. So with the synthesis of a biomolecule, we have two separate monomers, and we have the components of water that are removed. So we have the hydroxide from one monomer, the hydrogen from another, so H2O combining to form water, and we see this bond that's formed between the two monomers. That is a synthesis reaction, and dehydration reaction is a type of that. Just the opposite of that is if we had monomers that are joined together and we add the components of water. And so to break this bond in between them, this is a hydrolysis reaction because we're adding water. And we see that it's just the opposite of the dehydration reaction. This is degradation, or decomposition reaction.